Hello. I think the microphone is working well. I think we will start in a few seconds. Yeah. I guess we can start. Okay. Thanks everybody for coming. My name is Nicholas. I'm here together with Tian. We are going to present a workshop on NLP for ESG investing.
There's still a lot of people at coffee, so it might take a few minutes.
Okay. Should we start anyway, or? Okay. So yeah, I will redo that in a few seconds. Of course, maybe you can. Cool. Hello. So this time, I think we will start for good. Maybe we'll have some more people coming, but let's kick off the workshop. So thanks a lot for coming for this last session of the day for Building Bridge. So I'm Nicholas. I'm here together with Tian. So we are going to introduce some concept of NLP dedicated to sentiment analysis extracted from company reports with a strong angle on sustainability. So to give you a bit of context, so Tian and myself, we are employees at RAM AI, so a Geneva-based asset manager that was founded in 2007. So we both work on the systematic equity desk. So we are running long-only and market-neutral strategies on various regions, all market cap segments, with a strong emphasis on machine learning techniques and sustainability. So we run Article 8 and Article 9 funds with a strong exclusion integration approach. And today we will discuss some of the technology we use to extract information from non-structured data. So just to give you a quick overlook of the bios of the team, so you know who you're speaking with. I'm Nicolas, so I'm a portfolio manager and researcher for the funds. And Tian is a quantitative developer and analyst specialized in NLP. So as I was explaining, so at RAM we have a strong emphasis on sustainability. So on all our systematic equity products, we have a full process of exclusion and integration. So we put here, I could spend 1 hour explaining all those details, but it's to give you a quick overview of what is being done in our funds to achieve a sustainable profile. So it goes from classical revenue-based norm and value exclusions, good governance assessments, environmental and social objective promotion by promoting PAIs, like a sustainability profile overview. And then we have a full ESG integration based on deep neural networks. Finally, an ESG optimization process. So I'm not here to spend too much time on that, but it's really to give you a context on everything that is possible to do today with the right approach and the right technology to make a fund sustainable. So all our process, because we are 100% systematic, relies on a lot of data. So as you can imagine, for all these steps that are quite different, so from revenue breakdown to PAI's integration. So for our Article 9 funds, we also have a strong DNSH approach. We really need a lot of data points that we source from many different providers, depending on if we're talking about environmental data or more governance or more social. So on this slide, we show you the different type of sources that we have. So from financial report to sustainability reports. We also need agency ratings, NGOs, and revenue breakdown. All of these data are structured data, meaning that they come in the form of numbers that are easily manageable. It can easily be used even by discretionary managers in Excel tabs because they are figures, so that it's quite straightforward. It is very useful for us to have this data. It allows us to have a very nice exhaustive, well, not exhaustive view, but a very nice view already on the company. So, for example, we managed to do a multi-step governance assessment thanks to this structured data with figures like the independency of the board, on some controversies, on how the labor is managed, and all of this with, again, structured data. We also have an exhaustive set of structured data to measure carbon impact and carbon footprint of the companies, which is very useful to decarbonize our portfolio and our locations. It's also useful to do an integration indeed, so as we show on the chart here, we do find some interesting return prediction for low-emitting companies if you look at it at the sector level. So we have published a paper on that showing a strong correlation between operational efficiency and carbon emission. So again, this structured data for carbon is very useful for both decarbonization and integration. So the topic today being non-numerical data, we're just giving you a few reasons why structured data are not enough today to have a truly responsible and sustainable allocation. So first, numerical data are just partial picture of a firm sustainability profile. So if we talk, for example, about carbon emission, the firm can have well, limited carbon footprint, but at the same time, this metric being more and more recognized as important, companies can still try to hide other information on their sustainability profile, not reporting on everything they do, and that can damage the environment. And this kind of corporate behavior is called greenwashing. So for us as quants, we have the necessity to cross-check all the claims that companies make on environmental issues. And this kind of check cannot be done only on numerical data. You need more data sources. For another issue with structured data is that there are often delay in how we receive them, because structured data are often going through a third-party vendor or from the company themselves or from an NGO. So there is always a kind of a lag between what the company does and when we actually get the data. So, yes? Oh, why not? Yeah.
So when you say that there is like okay, sorry. When there's like the emission of the company, but maybe not all of the emission that they're reporting, and then I mean, just to get a bit more practical, how can you compare it with like non-numerical data? Just to give an example that allows to understand better.
Yeah, so typically that would be a company reporting only on scope 1 and scope 2 and not reporting yet on scope 3 because it's well, less or reporting with kind of subjective approach to appear well. And so you need to be beyond this data and see, for example, we'll give some example, but on the news, maybe some NGO published a paper in the news saying that the scope 3 of this company is certainly terrible. They don't have the exact number, but you can have discussion about it. You can have social media talking about it as well, on LinkedIn, for example. So it's just the figure would be considered as okay, but maybe there is something behind. And the whole idea is that a lot of figures are controlled by the company. So typically scope 3, the company will typically decide what it publishes. And we need to go beyond that and find information that is not directly controlled by the company to give an extra layer of information that would be less biased by the subjective approach. So another, so on top of getting more information, there is also a need to get more timely information. So again, all this structured data is very useful, and it helps us really have a nice integration. But for example, in the case of severe controversies, it's very important to capture the controversy as soon as it happens. And by waiting for third party to integrate it in some databases, we might spend 1 week, 2 weeks, or 3 weeks before getting the information. With well, the infrastructure we have, we think it's important to be able to capture this kind of controversy in a more timely manner to avoid like tail risk of getting unsustainable stocks in our selection. So we show you here a list of databases that we are currently using or that we aim to work on in the coming months. I will take a few examples. So earning call transcripts. So it's a management discussion of the company results on a quarterly and annual basis to see if, for example, the company made a commitment to net zero a few years ago and see how it is translated into actions and how it is discussed by the management during the earnings calls. We can look at press release. Something very interesting. Something really interesting would be patents. So to see if the company is developing green tech, for example, to decarbonize. So again, if the company is not reporting on Scope 3, at the same time they are committed to net zero, it would be a very nice information to see if they developed some patents to bring them up to speed to be able to get the needed decarbonization. So I was saying news flow, that's really a great source of information that we can capture, social media and NGO reports. So all of these data are a type of unstructured data. So they're text. So compared to structured data, it's harder to manage. So you don't receive them in an Excel format or a CSV format. And it needs some technology to handle and to be able to extract the information from it. So what we commonly use is natural language processing, so NLP. And so we have here today Tian that will take you step by step on how to get started with NLP.
Thanks, Nico. Hi, welcome. And I will continue the presentation. And let's see. Oh, sorry. Okay. Here's a table of the following content. And we will talk about NLP and its application. And here I put a QR code. Guess what it is? So it's a Google Colab environment. We put a demo there. Unfortunately, because we don't have the internet access on the podium, so we put a demo there. So if you scan it, you can visit the demo and the code there. You can even run it online, so for free. And also at the end of the presentation, we will also talk about the demo we put on there. So to guide you through the code to explain the content. And no worry, no hurry to scan it now if you I think you need a Gmail account. You can use your own account to access it. Yeah. No. I think no. You noticed that? Sorry. Sorry, I didn't realize that. I thought it was open. Oh, sorry. Yeah. I see. Sorry. Yeah, maybe you can help me here on the list. Yeah, I think it's good we have a colleague here and to help. Okay. Yeah, sorry. Yeah. And anyway, we have time. We will have time to discuss about the demo there, so it's okay. And so I will talk about natural language processing, and so during our presentation, it's a bit technical, but we will try to avoid complex mathematical there, because we think it's better to give the intuition behind this technique. And because if you look at the recent papers, even many complex models, they started with some very simple idea, a very simple intuition. So I think it's good to give the intuition, and then it's easier for people to understand how this technique evolves over time and where it potentially can go. And yeah, and meanwhile, another point I would like to mention in the beginning is that we talk about natural language processing, we will talk about the sentiment, but actually the technique we will present is not specific for sentiment. Actually, it's a very generic technique. It means that it can be applied for to different scenarios or different information extraction and so on. And also during our presentation, we will show examples where we use not only sentiment, but also the textual embedding of this combined information from text to improve our strategy, to improve the performance of our strategy. So we will see an example there. And I think that's, yeah, all this point I would like to mention in the beginning. And regarding the content, I will first talk about the tech itself. And I will mainly talk about 3 points. And these 3 points are ordered in time order from the rule-based and the statistics-based and the machine learning-based. Somehow they represent the evolution history of natural language processing over the past few decades. And then I will talk about the application, especially for sustainable finance and about sentiment, and I will show an implementation demo on this Google Colab. So I know it's somehow always difficult to give a presentation in the last round of session in a conference because people are tired and even hungry. So I hope my presentation in the following can cheer you up. Okay. And meanwhile, feel free to interrupt me anywhere if I'm not clear. And yeah, so feel free. Okay. Sorry.
The Google Colab should be fine now. Just
okay.
with the link, it should be possible to connect.
Okay. Yeah, I think. Oh, good. Let's. Oh, sorry. Go back. Go next. Still following Nicolas' presentation, I will first talk about the structured data and unstructured data. So we know structured data is very easy to understand. It's just a spread, including numerical values. We have different columns and yeah, and values. And regarding unstructured data, is not only about the content or the format. For example, in this case, I put a piece of financial news. It has headline, it has content, and yeah, it's obvious that different news have different. The content has different lengths and different, yeah, some content or even figures and so on. And meanwhile, another unstructured thing is that it's about the volume. If you look at the figure on the bottom right, that's a figure showing the volume of different types of news. You can on the left-hand side is the news about company earnings, and on the right-hand side is about on the most right-hand side is about antitrust. So you can see this very imbalanced distribution of news across categories. So, and meanwhile, another point is on the temporal dimension. And you know, for example, for some big companies like Google or Apple, maybe during the earning season, it can receive hundreds of news regarding their new performance or new results or their new product release. But for some small companies, you can imagine the amount of news they receive over time could be very small amount, very marginal. So this unstructured thing lies in many dimensions of the data. And meanwhile, because in many cases we need to do quantitative analysis, not only for systematic fund, but also for some discretionary fund, they also need to do some quantitative analysis. And in quantitative analysis, we need some numerical values, right? For example, in this case, I still have to put some formula there, but very simple. Normally, we need some numerical values in the format of vectors. It's a d-dimensional vector, for example, x, and the target is y. Y is normally one-dimensional or several dimensions. And we need to build some either linear or nonlinear models to quantify their relation and to understand their relations, right? But so then, obviously, there's a gap here, because from this unstructured data or text, there's no direct, let's see, direct link between the raw data and the tool we use to analyze them, right? The textual data and the quantitative analysis, we need some transformation to transform textual data into kind of structured numerical values for the downstream analysis. So this transformation, I always misuse, okay. This transformation is where the natural language processing comes to play. So right, this is kind of the motivation of using natural language processing in this context, okay? And next, also be aware of that natural language processing is not a new emerging technique. Actually, it has existed for quite a while. And on the left-hand side, I show mainly three different periods of NLP development phases. The first one is the very traditional one, I would say. It's a rule-based method. The second one is more recent. It's about using statistical method to model natural language processing. And the third one is about the most recent one is based on machine learning. And on the right-hand side, I show some code. Actually, it's very interesting to see that this not very young technique has some interesting relation to here, Switzerland. You see the code on the top right-hand side. In the early 19th, actually, a Swiss linguist professor named sorry for my pronunciation.
Ferdinand de Saussure.
Yeah. And he somehow introduced the concept of language and the science. Right? This is a very disruptive idea, I guess, at that time. And now then, after that, we have computers, we have cloud computing, we have machine learning, we have all these fancy hardware and software infrastructures to support the development of natural language processing. And now people have the ambition here is that we aim to make computer somehow understand the content of human-generated document. And so next, my presentation will mainly focus on the three different phases: the rule, statistics, and machine learning. I will introduce some typical techniques and examples from each phase, and then we will I think that's okay. First, let's see the rule-based one. I will spend very short time on the rule-based one because, to be honest, I'm not an expert on this. And meanwhile, it's a bit traditional, so actually, it's not very somehow straightforward or easy to apply to current applications. And the focus of rule-based method is to do some very you can imagine this rule-based analysis on text. For example, on the most left one is the lexicon analysis, and also the syntactic analysis. These two types of analysis is aimed to somehow pass the structure of language to understand the relation or dependency between each word or tokens in your sentence. And I will give an example here. For example, I give two examples here. And on the left-hand side is an example to analyze the sentiment direction of certain event in finance. For example, this one is about the company expects its EBIT in 2013 to increase a number from the previous year. So by this kind of analysis, it aims to identify the correspondence between certain pairs of words in your sentence. So for example, it identifies that the increase corresponds to EBDT, and if we put these two words together, it means this is positive somehow result for this company. And on the right-hand side is another example. It's called POS tagging. It's kind of tagging to identify the role of individual word in a sentence, and meanwhile to identify the relation between this word. For example, if we look at the middle one, a hearing is. So the is the root of this sentence, and from is it also related to hearing and the schedule, because the hearing and the schedule is the noun and the verb of this sentence. It's the two main part of this sentence. And this is a rule-based analysis. So you can imagine. Oh, sorry. Okay. And this type of analysis is, I would say, is more still discretionary based, because essentially what we get from this type of analysis is kind of it's still not numerical values. It's still kind of let's see, expression or some language to describe the relation of another text. So it means that the result, the output, cannot be directly used by quantitative models, right? And meanwhile, this type of analysis need a lot of domain knowledge. For example, in this case, I use English. If you are if you are linguistic in French or in German, then you need a lot of in-depth understanding of the knowledge itself, right? And this is it's not a straightforward. It's not that straightforward for general researchers And then next, we go to the statistical-based method. So after the rule-based period, some researcher with a statistical background find out that essentially, this human language can be still interpreted from the statistical perspective. It means that given this unstructured data, no matter it's news or transcript or even social media data, we can somehow have develop some statistical method to describe the distribution of word in your text, and then to further extract some information or features from this distribution. So in this way, we can somehow transform the text into some structured features. Then these structured features, or we call it textual features, can be used for downstream quantitative analysis. So that's the basic idea of statistical-based natural language processing. So here I will maybe use three examples. One is the language model. The second one is topic model. And the third one is linguistic feature extraction. So through these three examples, we will see what type of numerical features we can extract from text by this statistical-based method. The first one is about language models. So here I use a very famous picture, I guess. It's about the Tower of Babel. I think you know it better than me because I'm not. I don't have much knowledge about these religious things, and I think that the idea here is that, although people speak different languages, but from statistical perspective, there could be some common underlying pattern in human languages. And what statistical-based method does here is to model, we call it the generative model of human language. So for example, so what I mean here is that, so imagine this is a sequence, a sentence, let's see. And here we aim to build the the probability distribution of this sentence. The sentence is a sequence is from W1 to Wn, right? This is the joint, we call it the joint probability of this sentence. And by a very simple decomposition, here we make an assumption that each word in our sentence is depending on the previous word in this sentence. It means, for example, when I say I'm speaking here, and when I say until I am, and the next word speaking depends on what I said before speaking, right? This is the sequential dependency in a sentence. So basically, the idea is that here I use this example. So if I say the company expect is this is the part we observed, right? And then the next word, what would be the next word? It could be EBIT, could be return, or could be, something else. Yeah. So by statistical method, people aim to build a model to capture this probability distribution of text. And so imagine that assume that the ideal case is that if we have a powerful enough model to capture this probability distribution, and then we can use this model somehow to generate text. That's why here we call it's a generative model. It means that if I give let's say a half sentence into this model, and then this model will tell me what would be the next word or next sentence, right? Then by this model, we manage to have to generate synthetic human language. Yeah, so that's the key idea of language models. And later on, we will also see the language model in the context of deep learning. It achieved massive successful success in many applications in recent years. So that's a very mainstream technique we are using, and we will talk in the presentation. Okay, and here is about the next example. Oh, I used the wrong one. The next example is the topic models. It's a little bit complex, but still it has some beauty of both mathematical models and language, human language processing. For example, let's first look at the purpose of this model. So the purpose of topic model is that imagine you receive a set of documents. Let's see. You don't know, you have no idea about what document, what topics, or what let's see, general content this document are about. Then the topic model here is that by apply this topic modeling on this set of document without prior knowledge, it is aimed to characterize the topics discussed in this document. For example, if I'm given a set of news articles without knowing what they are about, and by applying this I don't need to read through the news read through this news, and by applying this topic modeling, it can tell me that this set of news is mainly about 3 topics. Could be food, could be sport, could be politics. Yes, right. So, but how to achieve this? So, mathematically, we call it latent dirichlet allocation. So, it's similarly here is that we have a joint probability distribution. Z represent topics, and W represent the words we can observe in this document or in this set of news. And then by using some fancy mathematical modeling and optimization techniques, we managed to get this. I always use topic distribution. So let's let me give a brief look at this result. What does the result look like? So imagine we are given this set of news articles. And then the result would be like this. If we look at the middle figure, it shows 4 different topics from the document, from the set of news. And each row represents, and for each topic, we see it has 10 different words. And these 10 different words represent the key word corresponding to this topic. For example, if we look at topic 1, it's about black stone or bid and bidders and bidding and auction and so on. And if we compare it to topic 2, it's about the settlement, parties, termination, legislation, connection, and so on. And or maybe we should compare it to topic 4. It's more, the difference is more obvious. So topic 4, we see Google, Apple, and yeah, all these tech companies. So you see, they represent. We can somehow we can interpret here that the topic 1 represents some financial companies or financial yeah, some traders and so on. While topic 4 represents some tech companies. Yeah. Yeah. Mm. Yeah, that's a good question. And here the topic is more about the global information from this set of news. Another output we can get is the topic, we call it the topic distribution of each piece of news. It means for given one piece of news, which topic is more probable for this piece of news, right? Yeah, and here is, but then we need to understand what this topic is about. Then we can refer to this table to say, hey, if for this piece of news is more about topic 4, then for topic 4 we see this set of keyword. Then it means this news has high probability on topic 4. Maybe it's about tech companies. Am I clear? Okay. Yeah. Yeah. Sure. Mm.
Just a quick question. Oh, sorry. So that's my question. Do you need to know the topic beforehand, or you give a corpus of text documents and it will learn and cluster like those documents according to topics?
In this case, it's fully unsupervised. We say it's without any prior information, and of course there are other type of technique called semi-supervised topic modeling, where you can give some prior knowledge information. Yeah. So it's fully possible to integrate prior knowledge into the process. And on the right hand side, where I give another plot showing the top 30 most relevant terms or words for a topic. Similarly, it shows that this topic, this actually is called word distribution for each topic, right? And next, here I give the example to the question. So here you can see on the left hand side, this is one output from topic modeling. Imagine in the beginning we give 9 different documents to the modeling, and then the output would be like, for each document, I get a topic distribution for this document. And it tells you, for example, for document 1, topic 2 is more probable for this document. And then by refer to this table, you can check what topic 2 is about. Yes. And this is topic modeling. And the last one is about it's more simple. It's linguistic feature extraction. Actually, it's purely statistical based. So the idea here is that actually it's benefit from the computational linguistic, because in computational linguistic researchers there developed different set of lexicons for different domains or different applications. And by leveraging these domain-specific lexicons, so we can extract certain information from text. And for example, in this case, it shows some linguistic features extract from financial news. And each row represents a news for a certain company. And by using the lexicon, by using different lexicons, we can get a set of features from a single piece of news. And for example, here it used the lexicon for sentiment, whether it's about positive sentiment or negative sentiment. And also it has the features about certainty or uncertainty in your text. So the method here is quite straightforward, because so given the lexicon, which is basically a list of words, that can represent, for example, very positive sentiment or very negative sentiment, then we just apply this list of words to the text to count. Let's see, for example, how many positive words appear in my text, and then do some simple statistics to get a score. Yeah, right. This is a very straightforward idea. And so far, I think we talk about the statistical method, and also in the beginning rule-based method. So recall that the intuition or the motivation here is that we need some numerical features from text for the downstream quantitative analysis. So by using this statistical-based method, we can manage to get some numerical features. For example, these topic features or these linguistic features, and so on. But there is a very significant drawback here, is that these features still lacks semantic distinguishability. So what I mean here is that if we look at the example on the bottom right hand side, I gave two groups of text. Let's first look at the first one. The first one is Nokia hopes its engaged mobile phone will boost sales and attract younger generations, right? And it's kind of positive news for this company. It's about a new product, and it's about boosting sales, right? So that's why I put a red color for this piece of news. And next, let's look at the second group of news on the bottom and to the bottom. The first one is HBC and BCS upgraded to outperform from peer performance and peers terms. And also the second one is the Bs upgraded to overweight from equal weight and think equity. So why I put this group of news together here is that we can see both of them are kind of positive about companies, but actually they are talking about totally different things, right? One is about the product and the sales, and one is about the grade from third parties, right? But if we just look, if imagine we just extract sentiment from this text, and all of them will have positive sentiment, but actually they are about different content. So that's kind of lack of semantic distinguishability. And why this semantic distinguishability matters here is that for some downstream task, we still need to further distinguish distinguish where this positive, let's say, sentiment comes from. We have to distinguish it's either about a product or about fundamental aspect of companies or from other aspect. And similarly, for negative things, we need to distinguish them in order to understand or quantify the relation between different events to their, for example, performance and the risk and so on. So that's
and it's specifically important for sustainability in our context.
Yeah, true. Right. And the second, let's see, shortcoming here is that this both rule-based or statistical-based method lack the end-to-end development, let's see, support. So what I mean here is that, so given a set of texts, we need to first do the feature extraction by using either rule or statistical-based method. And once we get a set of features, or we finish this kind of transformation, we can feed these numerical features into downstream task. But actually, in many applications, we need kind of end-to-end development. It means that we, from the raw input, raw text, to the end target variable, for example, return or risk, we need some end-to-end development and optimization process. So yeah, that's another. This is another drawback of this two method. So next, we will go to the more exciting part, I think, at least. Yeah, sure.
Approaches that you just presented, language models, topic models, and linguistic feature sorry.
Yeah.
Thank you. The three models that you just presented, the language models, topic, and linguistic, they're all about sentiment analysis, or, I mean, you get a positive, negative at the end? No, we just saw that you got numbers, right? So
yeah.
So what is the link? But you said a drawback is lack of semantic distinguishability.
Yeah.
So is that a drawback of these three things, or because we saw numbers so far, right? We didn't see positive and negative, but then you said grouping. So could you clarify that? Is that clear where I'm coming from? So it's a bit unclear. The drawback that you say that it's a semantics distinguishability with the type of output that you get from the tree statistic-based method that you just presented.
Yeah, that's the general drawback for all.
For all of them.
Yeah, for all of them. Okay. Because even for topic modeling, although we get some, let's see, this topic word distribution, like I showed here. This is the topic word distribution, but actually, that's why sometimes we still need to go back to the mathematical thing, because essentially it's based on statistical. It means that it's based on the frequency or concurrency of word in your text.
Okay.
Right. So if two words often appear in your document, then they say, oh, maybe they belong to the same group or same topic. And if this word appears more than other words, then maybe. But you see, it's still purely counting based, right? Simple counting based.
Yeah. Okay. So it's about the methodology, not the output. Okay.
Yeah. Exactly. Yeah.
Okay. And the output end to end that you the end to end drawback, then the second one that you were referring to.
Yeah.
That means that these techniques, they give you they don't give you numbers. Is what you want is numbers, or?
Yeah, maybe I'm not clear here. So what I mean here is that we give the number. The process of getting this number is kind of independent process. We just get a number no matter whether this number is really useful for my downstream task or not. Okay. We just get a number first, and then we do the following things, right? And what we will show, and you will see in the next, is that in the modern deep learning-based method, we prefer some end-to-end solution, which means that from the very beginning, we tune the model or tune the process to be favorable for my very end task, very end task variable. Yeah. Yeah. Okay. Okay. We will see. We will see. Yeah. No worry. Yeah. Yeah.
Or also with ESG news, and I mean, in which proportion?
What we present here is the generic tag, and in our case, we applied to both generic news and more ESG specific news. Yeah. Yeah.
In general, we try to have a same approach for fundamentals and sustainability-related topics. So it's really a quantitative approach that we apply across different data sets. And so we have pure, for example, news flow data sets that are where we get information from both ESG and non-ESG. Then we will start looking at sustainability reports, where it will be purely sustainability, but with the same technique and same approach.
Excuse me, how much computer power do you use? How much computer power do you need before we even get to these current sophisticated things, just to do simple stuff like this?
That's it's not much. So far, for the method I have talked so far, it's rule-based or statistical-based. Your personal laptop is okay. Yeah, it's okay. And so far we haven't really entered the real computing intensive method. So next we will see some real computing intensive method. Yeah. For example, for the topic modeling, if you run it on your laptop, if you have, let's see, 1 million pieces of news, I think it just takes a few hours. Yeah, it's not, yeah, I think it's, yeah, affordable at least, yeah. Yeah. Okay, I think, okay, we'll go ahead. Yeah, all good? Okay. Let's go ahead. Yeah, here. Okay. Okay. Now we are entering into a new era. It's a machine learning based method, or actually it's more deep learning based method. So first, I give a interactive example here. So to illustrate the idea. So the key idea of machine learning-based method is about the concept, we call it text embedding. So in short word, it means that with text embedding, we aim to define semantic meanings of human language by coordinates or vectors, numerical vectors. So what does this mean? So here I give an example. So if we look at this table, we have 3 rows, and each row has 4 columns. And if we first look at the first row, it corresponds to Italy. And if we use 4 digits to represent the word Italy, and according to which column the coordinate it is we fill numbers. For example, for Italy, if it's a country, then we give 1. It's not a capital, right? So we give 0. And then it's not Greek, 0. It belongs to Italian, and then we give 1. And similarly, we do it for Rome. Rome is a city. It's not a country. Then 0. It's a capital. 1. It's not Greek. It's Italian, right? And for Athens, 0 is not a country, it's a capital, it's Greek, and it's not Italian. Okay? Now we have this numerical representation for 3 words, Italian, Rome, and Athens. So don't ask why, just assume that we are given this representation of each word. And then now I need your help. So try to do this calculation. Italian, if we do the calculation, Italian minus Rome plus Athens, what would be the result? Imagine from both mathematical and the semantical perspective.
Like X is for every column, or X that is the sum of all the columns?
And I can tell you X can be either a number or be a word here. You can tell whatever you want. You can tell a word. Where? Value 2. Value 2, you sum it up? Or value 2, why is value 2? If you don't sum it up, you try to interpret interpret the role from semantic perspective. What would be the result? If Italian without Rome, but we add Athens, then what would it be? Huh? Exactly. It's Greece. Why? Let's do this. First, let's do this calculation, right? We just calculate based on the number of each, based on the, let's say, the vector of each word. We Italian this row minus the second row, and then plus the last row, we get these numbers, right? And then let's try to interpret these four numbers. First is the country, right? Second is not the capital of this country. Third, it belongs to Greek. And then the last one is of course is not Italian. Then what would it be? It's a country. It's not the capital. Then it represents Greece, right? So it means this last row, these four numbers, is kind of the numerical representation of Greece in this very specific, let's see, data setup. In the very specific example, right? So here I just give the example of how, let's see, conceptually we can use numerical representations to represent text or word. And meanwhile, interestingly, this representation can carry some semantic relation between these words, right? This is the motivation. And next, now we need to look at some technical part of this intuition. So here, the thing becomes more complex, and you can say here, we need 3 components to achieve the motivation or achieve the intuition we just say. So we need data, right? So imagine, so in the previous example, we just have this 3-word and the toy example. But imagine for general language, as a general English language, we need huge amount of data to build this kind of representation, right? And meanwhile, here, not only we call it large generic corpus, for example, from Wikipedia, and also we need some domain-specific data. So later on, we will show why this domain-specific data and both this type of data are very necessary and important for the success of text embedding. The second important component is model architecture. So what does model architecture means here is that, so given this word, or given this word, or their numerical representations, we need kind of computation process to, let's say, to characterize their relation. For example, in this case, it's just some minus or plus and so on. But we need that, but this is a very simple case. We need some more, let's say, more advanced metrics to reflect either the similarity in text or the relevance in text. So that's where we need some model architecture to model the similarity or relevance in text, right? To do this, let's see, quantification thing. And the last component is about training. So we feed the data, and the model architecture will do the computation to quantify the relation in text. But this is not enough, because we also need the computation or the characteristic, the similarity or relevance calculated in this model architecture to be optimized. So imagine if we just randomly give some numerical vectors for each word, then we calculate their similarity, so this similarity is not accurate at all, right? Then we need some training process to make the calculation of the similarity or relevance to be as accurate as possible, and close and to the real, let's see, how to say, and accurate as possible. Yeah, that's why we need a training process. And also, one point I would like to mention here for training is that, so the recent success of this textual embedding or machine learning-based natural language processing techniques is highly attributed to the automatic a tool, we call it automatic differentiation. So it's a tool that when you have a model, mathematical model, when you aim to optimize it. So traditionally, when you develop a model, when you aim to, in order to optimize it, you have to do some manually derivation of gradient in this model. You can imagine once you tune your model a bit or change your model architecture a bit, then you have to redo the derivation. It's very time consuming and very need a lot of effort. But with this automatic differentiation tool, this gradient derivation step can be done automatically. So it means that it significantly speed up the development of different models, because people can quickly iterate to try and trial and test and to improve the existing models. So this is a very important tool for nowadays machine learning. And the next, I will mainly present two types of textual embedding. And one is called word embedding, and second one is called contextualized embedding. So from the name, you can see somehow you can see the difference. So word embedding is just embedding for individual word. For each word, I give a different vector representation, right? And for contextualized embedding, is more about the context, more about the precision or the role of individual word in a sentence or in a paragraph, right? So, and still, both of these two types of embeddings highly rely on the three elements which we see here: the data, the model, and the training. Yeah. So actually, it's different combinations of choices in the three elements lead to these two types of embeddings. Okay? And the next, first example, let's see the text embedding, or the word embedding. So it means we have, So the idea here is quite, it's also not, it's straightforward actually. So the word embedding here is that, imagine when we look at a sentence, let's say the firm said they didn't believe the contract to be that important to the sales, right? So the idea of word embedding is that, so in order to model the relevance of word in a sentence, so the representation of word should have some predictive power regarding the word, regarding the surrounding word. For example, if let's see, in this case, if I choose, let's see, the contract, then if I use the representation of word contract, I should be able, the model should be able to somehow predict the word surrounding contract. In this case, using the representation of contract, it should be more probable to predict like the important or sales than other word not in this sentence. So this is I'm not sure I'm clear here. Yeah, it's about the. So imagine, let's see, we just randomly give each word a vector, a vector, and then in order to make this representation carry some semantic information. So the task we believe. And then sorry, let me rephrase my sentence. So in order to make the representation carry some semantic information, so the task we use to train the model is to let the representation of one word can be used to predict the word surrounding the current one. Yeah. So let's look at an example. Maybe it's easier. So on the example on the right-hand side, this is the representation from the model already learns from the data, and then so given this representation of individual word, we project individual word to this two-dimensional space. If we look at which one is either, I'm not sure it's clear enough for you. Maybe the one on the top left. This one is about investment. So let's look at the investment. So first I project the investment into this two-dimensional space, and then I project some other word with into the same space and the investment, the word investment. You see, all this word close to the word investment in this space, in this numerical space, also have some semantical relevance or closeness with respect to investment. We see investment is the center, and then we see insurance, an investor, and hedge, and equity. All these words are close to investment in this numerical space. So it means the representation of this word show some closeness and coherence in this numerical space. Okay. I think we have to hurry up a bit. This is the idea of representation. And next, we see the contextualized embedding. So the different thing here is that the contextualized embedding is aimed to model the more contextual information. So I use this figure to illustrate. So imagine on the left-hand side, this is the input. So imagine similar, still we use this sentence, and we first project each word into a numerical vector. So this vector can be either fully random, or can be from your already trained word embedding. And then this set of vectors goes to we call it transformer structure, right? But this transformer is not the one in the movie. I think yeah. And And then, if we look at on the right-hand side, if we look at this figure, so it shows that for individual word, it characterized the different relevance of word in this sentence with respect to a certain word. In this case, it's a firm. So you can see for firm, in this sentence, the contract, the sales are more relevant to the word firm. And the other word, let's say they, did, not, they are not. Their color is very light, representing less relevance. Okay, yeah. And we have to speed up a lot, I guess. Sorry. And then, yeah, this is the contextualized embedding. So actually, contextualized embedding is highly from the, we call it large language models. It's a very popular and successful models in recent years. And the idea here is that we have we call it pre-trained process to train these large language models on a very general and large language corpus, normally Wikipedia. And then we can fine-tune it, means we further train it on some very small but very application-specific data set to improve the performance of this model on these very specific applications. And next slide. Okay, about the application. Oh, finally we come to the application. And then maybe one question you may ask here now is that, so even if we are given the representation, we get the representation from certain models, what can we do with it, right? This is the final goal. So then in this case, for example, we are given the representation of this set of sentences. In the very simple case, we project them into 2 dimensions, right? We have this, each point represent to one sentence in here. And the application scenario here is that if we add another dimension called y, then we expand this space into a three-dimensional space. And it's ideally, in this three-dimensional space, including the representation and the target, we can separate the point, separate the text of different, let's see, information or different relation to the target. And then in this space, it will be very convenient for us to develop, or very convenient to somehow to distinguish or to identify different patterns for the input text and with respect to the target y, right? This is the somehow the application scenario of using embedding. And yeah, now I show examples. For example, here, although this presentation is about sentiment, but actually, in our case, we also use it for ESG controversy detection, because in this case, we just need to change the target variable from sentiment to ESG controversy. Then, yeah, we can have different applications. And the next, yeah, that's another application. We use both sentiment and textual embedding in return prediction in our quantitative process. So we can show that by adding the sentiment, by adding both sentiment and textual embeddings, actually we can get even better performance than using just factors or using only sentiment. So this is yeah, in the real backtest example. And the next summary, yeah, summary actually is about. I think the last takeaway message you can get here is that although we talk about a lot this mathematical, this model, and also the data and these complex things. But in the world of Python, things is much easier. Just need import. All these things, putting them together, we just need to import the proper library, and then do the coding. So don't be afraid of the things we have present here. All these fancy things doesn't matter. You just need to remember report. But of course, I encourage you to understand the math under the hood, because in real applications, it's very important. It's also very important to fine-tune your model to make full use of the power of your model. That's still need insight and still need, unfortunately, math. And then next, actually, I plan to show a demo, and that's a code. The last question I ask to you, who knows this code? Who this code from? If I have 5 minutes to chop down a tree, I'd spend the first 3 minutes sharpening my axe. It's from Lincoln. Okay. And then I show the demo. I showed here I prepare some tools you can use. On the left-hand side is the data set, where you can find some open data. Google dataset search is very it's well known, and the Ceres is a sustainability data provider. And on the right-hand side is the very popular tool widely used recently. We have the PyTorch with the machine learning or auto differentiation tool I mentioned, and all these natural language processing models I mentioned can be found from Hugging Face transformers. This is extremely popular in recent years, and we have some other tools. And
everything here is open source. And, even the data is freely available.
Yeah, and that's this example about how to query some data from Ceres regarding I think climate sustainability disclosure of individual companies.
Extract of 10K related to climate risk.
Yeah.
So that's really useful as a basis to try to extract sentiment from sentences to see if what the company discuss in the financial report is impactful, and if it's sentiment around it is rather negative or positive regarding climate.
Yeah. And another thing is about what we can find on Hugging Face transformer.
The one before is a database of PDFs or
so it's actually they use as a basis the 10K that are freely available, and they apply actually a first layer of machine learning of NLP to extract just climate-related sentences. So on the website you have to extract it's PDF or web-based. You can copy paste, but then you can also contact them, and they will provide the API to download the full.
So there is Okay.
The API is available on request, but we did it, and it's a really nice way to start building on sustainable.
And your demo does this, or?
The demo I already downloaded the data and put it in the you can download it. But
Thank you.
And then this is about the good thing of Hugging Face Transformer library is that it provides massive pre-trained or pre-saved models available by other researchers. So some of them are quite state-of-the-art performance. You can directly use it and further tune it to your own applications. So it's very convenient, very fast for your application, for your development.
When we're talking about compute power, actually the compute power is really necessary to train those models. But now for users, it's inferences, so there is no need for a supercomputer to use them.
Yeah. And also you can find some very useful data set there. For example, in our case, if we want our model to be better and financial sentiment analysis, then we can find there is some financial sentiment data set on Hugging Face. Then you can free to use. And then the last one, it's about the code. I planned to go through the code with you. I think now, yeah, you have to, yeah. Still 5 minutes? Okay. But I think, yeah. It's too boring. Yeah, okay. Yeah, wait, first let's see if we have some questions. Oh, yeah, sure.
So, I mean, like, very interesting, very powerful. I think that this can really increase dramatically. Thank you. This, I mean, very interesting, very powerful. I think this can really increase dramatically the coverage of climate ESG data. But this leads to my question. What about false positive? Like, I make an example to clarify what I mean. Let's say that we want to build, for example, like a portfolio of companies that have, like, for example, exposed to water, so like a water-themed fund. So, of course, for then we need to have a lot of water data, for example, water footprint, water consumption, and this is the data that, at least in my experience, sometimes is quite difficult to get. So we can use this kind of tool. But for example, if we get something wrong, it's possible that, I don't know, we introduce a value for a company that is like, I don't know, 100 times, 1,000 times bigger than it should be. This is going to be completely ruin the result of the portfolio. So I was wondering, how can you be sure that you're not introducing something that is going to ruin everything else?
Yeah. So the idea is not really to get a pure like water emission or water consumption data. It's more to, if you have the water emission data from the company that is self-disclosed, try to look in sustainability reports if they really are discussing that, or if it's well, not a major theme. In a patent database, if they developed a clean tech around water usage. In social media and news flow, if the sentiment around the water profile is positive or negative. But the aim is not to replace structured data, but to complement it with extra information. So then there is two approaches. Either you go on a statistical way and you believe your model will be right 90% of the time or whatever, and you diversify as much as possible. Or you add a discretionary layer if you want to be very concentrated, but then it will, for example, if you take a very small cap where there is no coverage from ESG ratings, then you can already have like a universe of 50 companies that have a very good water usage profile across the different data sets, and then have a more discretionary approach to verify.
And just to understand,
yeah. Yes, yeah, and for some metrics, you could have if you reach 90% of coverage on other unstructured sources, then you know that for some companies you miss structured data, but still you have a view on what to do. Especially, for example, for controversies. For the negative side, it's even more powerful because so you know at least that if they did something very negative about water emission.
Yes, so I was wondering if in the tool there was a way of maybe segregating the sources of the data, because of course, and especially when it comes to sustainability, negativity and positivity are very subjective, right? The same action can be viewed as unsustainable from the side of an activism, whereas, I don't know, a mainstream finance report will write something positive about the same product or action. So could we sort out the author, or at least categories, or how does it work?
I take it. Yeah, so actually it's by using a bit of all the text that Tian discussed. So for example, there is a topic modeling. So this is what we actually do on Newsflow, where we receive the news flow for every theme, and then we have a classification based on the text, and to know if it's ESG related or non-ESG related. So, and it can be even more granular. So is it climate related? Is it governance related? Is it social related? And so on. So there is this first step where you can, within your data set, identify which article, if it's a news flow data set, are specific on ESG. Then, as Tian mentioned, but it was still at the end, so it was a bit quick. So there is necessity to fine-tune the models. So basically, so the state of the art would be something based on a BERT that was open source by Google, that was trained on a general corpus, so such as Wikipedia. And then now you have researchers that have developed a BERT version called Climate BERT that was fine-tuned on sustainability reports, on TCFDs, and so on, that managed to understand the context of climate-related sentences and extract sentiment and engagement very precisely in the climate context. At RAM, we're going to take this further and fine-tune. Well, our aim is to fine-tune as much as possible for every need this kind of model. So training on very specific corpus to then get the context right.
Just want to say that I think the hackathon, the registration is closed.
Ah, okay.
So if you like motivate people, I don't know if it's possible to do a last-minute registration.
It is possible, yeah.
Okay.
We are important people. We can get you get you in. Yeah, maybe a word on the hackathon, Tian? Oh, yeah. Okay, so yeah, so tomorrow we're partnering with Open Geneva, and to continue this NLP series, we propose a challenge to build ESG controversy data set. So it's using a text that Tian mentioned, that text generation, and actually the purpose is exactly what we just discussed. So to fine-tune models to better represent a specific context. So in that case, ESG controversy, you need a lot of data to train the model to recognize it. So to classify, is this news article about controversy or not? So to find the data for that, it can be complicated. It has to be labeled as well manually. So with the new technology, especially a tech called GPT-3, it's possible to auto-generate synthetic news. And the aim of the hackathon would be to generate a synthetic data set of ESG controversy news to then train algorithm to detect controversies in real news flow. So if anybody is motivated, it would be great to have you on.
Yeah, I think we have to finish. And yeah, thanks for coming again. And I hope it's clear, maybe not, and at least you give some intuition of the techniques. And yeah, essentially I put a plot from Nicholas, generated by machine. It's a green city. So let's hopefully these techniques can work together to benefit the green things in the world. And yeah, and thank you. And yeah, thank you.
Thanks a lot. We are still here around for any questions. So especially for Tian, but.